Hi, welcome back to Calculus, AP Calculus, Unit 5. This is Lesson 5 about the second derivative test. There are two theorems that we can use to justify the existence of a relative minimum or relative maximum. Both of them had the word test in it. The first derivative test and the second derivative test. And that's the only thing you should use them for, is saying relative max or mins. Consider this graph. I want you to classify each labeled point as a relative maximum or relative minimum. Then, just using your intuition based on the shape of the graph, determine the concavity at that point, whether it's positive or negative, concave up or concave down. All right, let's see what you decided. Well, A and C are what we call relative minimums because they're the smallest y-coordinate in the neighborhood. And at A and C, F is concave up. B and D, however, are relative maximums. And at B and D, F is concave down. Well, that's exactly what the second derivative test theorem says. It says that if we have a critical number at C, then if F is concave up there, remember concave up would be shaped kind of like this, then we have a relative minimum. If we're concave down, we have a relative maximum. The theorem does have some important prerequisites that we have to establish. First, of course, C has to be a critical number and that F prime of C has to equal 0. Recall that critical numbers could also be places where the derivative is undefined. But if the derivative is undefined, then the second derivative test is not available to us because the second derivative would also be undefined, and we need the defined derivative. Second, the F needs to be twice differentiable on an open interval containing C. So we need more than just continuous or the first derivative on an open interval. We need it twice differentiable. And notice that there's no exception for the point C. So if F double prime of C is greater than 0, then C comma F of C is a relative. Think about it. We're positive second derivative, so we're concave up. And if we're concave up, we're shaped like a cup going up. We must have a relative minimum. And if F double prime is negative, then we're concave down, so we're shaped like a hill, right? Then this would be a relative maximum. At times, the second derivative test will fail to work, like F double prime would actually equal 0. And if it does, you just can't use the second derivative test, and you need to resort back to the first derivative test. All right. F is a twice differentiable function. Consider the following table of information about selected points of F. Classify each point in the table as either a relative minimum, maximum, or neither, and use some justification. Pause the video and give it a try. Okay, well, we can see that F prime of 3 is 0. And as we were told, F is twice differentiable. So it's twice differentiable on an open interval around 3. So we can apply the second derivative test. I can see that F double prime of 3 is positive. So that means we are concave up. So x equals 3 must locate a relative minimum. Now, F prime of 5 is also 0. And F double prime of 5 is negative, so we must be concave down. That means that x equals 5 locates a relative maximum. And again, what am I using to say this? The second derivative test. All right, F prime of 3 is equal to 1, so that doesn't tell me anything because x equals 6 is not a relative extrema. It's not a relative extrema because f prime of 6 does not equal 0. F prime of 8, though, that equals 0. And since f prime of 8 equals 0, we can use the second derivative test. And since f double prime of 8 is greater than 0, x equals 8 locates a relative minimum. Because, again, 8 is, f of double prime of 8 is positive, so we must be concave up. So we're shaped like that. Okay. Let's move on to another example. Suppose that f prime of negative 2 is equal to f prime of 1, which is equal to f prime of 3, which is equal to 0. Got all that? Given that f double prime of x is equal to negative x squared plus 2, let's classify x equals negative 2, 1, and 3 as locating either relative maximums or relative minimums. So we don't know the equation for f or f prime, but we have f double prime. So let's use that. Let's say f double prime of negative 2. Well, that is equal to negative 4 plus 2 is a negative 2. F double prime of 1 is 1. F double prime of 3 is a negative 7. Now, in reality, we should have to have some information about f double prime existing on an open interval around here, but I probably just didn't include that in the instructions, so we'll assume it's true. It's just a practice problem, right? So we can say here, though, that as long as we do have twice differentiability on open interval surrounding points, I can say that by the second derivative test, because f double prime of negative 2 and f double prime of 3 are less than 0, f has a relative maximum at x equals negative 2 and 3. And because f double prime of 1 is positive, f must have a relative minimum at x equals 1. Okay, let's practice using the second derivative test with an equation. Well, you know how to use the first derivative test, but let's practice the second derivative test. Go ahead and pause the video, find the relative extrema, and classify them with the second derivative test. All right, let's see how we did. The derivative of this equation is 3x squared minus x minus 2. The second derivative of this equation is 6x minus 1. Y prime is equal to 0. Let's see here. I think this is factorable. Yeah, it certainly looks like it. Negative 1 and plus 2, that would give me negative 3x plus 2x is negative 1x. So we have critical numbers at negative 2/3 and at positive 1. Well, y double prime of a negative 2/3. Now, I don't really have to actually evaluate this. I just need to figure out if it's positive or negative. So that'd be a negative number, minus 1. It's definitely less than 0. And y double prime of 1, well, this would be easy to evaluate, though, but that's greater than 0, right? So we can see from the equation that y is twice differentiable from negative infinity to infinity. So it is twice differentiable on an interval, open interval around our critical numbers, right? This twice differential means the second derivative is continuous everywhere. So we can use the second derivative test. So by the second derivative test, and we're just classifying the x coordinates, right? We don't have to plug it in. That's nice. So by the second derivative test, y has a relative maximum at x equals negative 2/3 because y double prime of negative 2/3 is negative, and a relative minimum at x equals 1 because y double prime of 1 is greater than 0. All right, let's use the second derivative test to determine whether or not f of x equals negative 2 cosine of x minus x has a local maximum or minimum at x equals pi over 6. Pause the video and try it. All right, this time we're just testing a single critical number, so that's going to make our job a little less work. The derivative of f would be a positive 2 sine of x minus 1. The second derivative of f would be 2 cosine of x. And f double prime of pi over 6 then is equal to 2 times the square root of 3 over 2, which is definitely greater than 0. So f has a relative minimum at x equals pi over 6 because f double prime of pi over 6 is greater than 0. And that's by the second derivative test. And we've already established that, but you know what we should do? We still haven't, we did not actually establish the preconditions. We need to make sure that f prime of pi over 6 equals 0. Remember, that's required. I forgot to even check that. So the sine of pi over 6 is a half, times 2 is 1, and 1 minus 1 is 0. Good. All right. That would have made a fool out of me there. All right, but we also need to say that f double prime exists on an open interval around that point. It certainly does. So f double prime, or I'll say f is twice differentiable on negative infinity to infinity. Okay, use the second derivative test to find the relative extrema of this function. Pause the video and do it. Okay, let's see how you did. F prime of x is equal to 6x squared plus 6x minus 12. F double prime then would be equal to 12x plus 6. F prime is equal to 0, and I can factor this, but first I'm just going to divide it by 6. That's going to make things a lot easier. And to get it factors is x plus 2 and x minus 1. So we know x equals negative 2 and x equals 1 are critical numbers. So here f is definitely twice differentiable from negative infinity to infinity. F double prime of negative 2 is less than 0, and f double prime of 1 is greater than 0. We can see that, right? Okay, so then by the second derivative test, remember, to say something's a relative max or min, you better say a derivative test, either the first or the second. By second derivative test, negative 2, comma, and then you need to plug that in. Let's see what that would be. Negative 8, negative 16, plus 12 is a negative 4, plus 24 is 20, is a relative max. And 1, comma, say a 2 plus 3 is 5, 12 is a negative 7, is a relative min. Why? Because f double prime of negative 2 is less than 0. Because f double prime of 1 is greater than 0. Yes, we just said it over there, but I like to put it in a sentence just to make sure that everybody sees it. All right, practice 5.6. Given that f prime of x is equal to g of x times x squared minus x minus 6, and this information, determine whether f has a relative maximum, minimum, or neither. And again, we need to assume that g is differentiable everywhere. So g is differentiable everywhere. And then we'll be able to conclude that f is twice differentiable. All right, pause the video and give it a try. Okay, let's figure out what happens at f prime of 3. Let's see if we can establish it's a critical number. Well, that would be g of 3 times 9 minus 3 minus 6. Well, g of 3 we know is negative 2, and this is 0, so yes, we've got that requirement. Let's get the second derivative of f, which is, product rule says g prime of x times x squared minus x minus 6 plus g of x times 2x minus 1. Excuse me. And as long as g is differentiable everywhere, this is twice differentiable everywhere. Questions like this are usually on the multiple choice anyway, so we don't really usually worry about too much about justifying. Excuse me. So let's figure out what f double prime of 3 would be. Well, g prime of 3 is 7. And we already know that that's 0, so that didn't really matter. And then g of 3 is negative 2. And then 6 minus 1 is 5. So this is clearly a negative number. So f has a relative max at x equals 3. Okay, on what intervals is f of x both increasing and concave up? Let's try that one. Pause the video and give it a try. Okay, so we need to know when f is increasing. Well, we take the derivative. We get that. If I solve it equal to 0, I can factor out a 6x, and I get 1 minus x. So x equals 0, and x equals 1. And you can see that if you plug in a 0, or no, excuse me, a number like to the left of 0, like a negative, you get a negative times a positive, which is a negative. And if you plug in a number in between 0 and 1, like 0.5, you would get a positive times a positive, which is positive. And then here we get a negative again over here. Let's find f double prime. Well, f double prime of x then is 6 minus 12x. And that is equal to 0. Let's see here. It looks like 1/2. Yeah, x equals 1/2. So this was f prime, and this is f double prime. So at 1/2 right here in between the two. And let's see here, 6 minus 12x. So if I plug in like 10, I'll get a negative number, and here I'll get a positive number. So where are we both increasing and concave up? Well, that must be on the interval from 0 to 1/2. What's my justification? F prime of x is greater than 0, and f double prime of x is greater than 0. All right, go ahead and do the next problem. Okay, and this is practice 5.8. I think this is our last problem. So that was all the problems there. Okay, let's go through it. Consider the graph of f prime of x shown in the graph for the interval from -6 to 6. For what interval is f continuous? Justify. Well, f is continuous on -6 to 6 because f prime is continuous. So if f prime is continuous, then we know that f is continuous. Because remember, that means f is differentiable, which implies that f is continuous, because that's one of the requirements to be differentiable. For what interval is f increasing? Well, f is increasing whenever f prime, remember this is the graph of f prime, is positive. So f is increasing on -6 to 1. Because f prime of x is greater than 0. For what interval is f concave down? Well, f is concave down wherever the derivative is decreasing. And this derivative is decreasing everywhere. So we're going to say f is concave down on this entire interval in question from -6 to 6 because f prime is decreasing. So f has one relative extrema on the interval at -6 to 6. What is the x-coordinate of this extrema? Well, that's x equals 1 because f prime of 1 is equal to 0. And we know that it changes from positive to negative. We're going to classify this using the first derivative test. Well, if you look at the graph, f prime goes from positive to negative. So by the first derivative test, we could claim that x equals 1 locates a relative max because f prime changes from positive to negative there. That's how we use the first derivative test. Well, how could we use the second derivative test? Well, quite easily. We said that f double prime was negative everywhere. So f double prime of 1 is negative. So by the second derivative test, f has a relative max at x equals 1. So be able to do both of those tests. Is it possible to determine the x-coordinate of either the absolute maximum or minimum on this interval? So we're asking, can we find the absolute max or the absolute min? Well, this graph is increasing in the entire time until it reaches 1. And then it is decreasing the entire time after that. So I'm just going to work it over here, but definitely we can say that x equals 1 locates the absolute max because f increases from -6 to 1, then decreases from 1 to 6. And we've already established, we could establish why. How do we know that? Because f prime is positive from -6 to 1, and f prime is negative from 1 to 6. But what about an absolute minimum? Could we establish that? Well, maybe with some more work, but it definitely appears as if it increases more here than it decreases there. But we would need to use some more calculus tools we haven't quite gotten to yet. But let's see if there's anything else that we could say about it. Yeah, we would have to have some more information about the endpoints. Later on, though, we'll have a way to actually answer that question. So we're just gonna stick with this, for now at least. Yes, we can establish the absolute max, and that actually is an acceptable justification for absolute extrema. That we have one critical number, we increase to it, and we decrease after it, so it has to be an absolute max. So another technique for you. All right, until next time, take care.